Good morning. I'm Dr. Sanjay Jain, Associate Professor in Mathematics, SPC Government College, Ajmer. Earlier, we have taken four lecture on continuum mechanics. Today, we are taking fifth lecture on continuum mechanics, in which we have studied cross product of two vector or Cartesian tensors. Earlier, we have studied uh, conical IJ Cartesian tensor or epsilon ijk permutation tensor and dot product. Okay. Vector or cross product of two vector. Earlier we have studied scalar or dot product of the two vector, and we know the dot product or scalar product is a after product they give us a scalar quantity, while in case of vector or cross product of two vector we get an again the resultant we get an a vector quantity. How we define this? Let the vector or cross product of two vectors A and B denoted by A cross B. In dot matrix, in dot product we have taken A dot B, but in case of cross product we have denoted A cross B and is equal to a vector C because it gives us a vector quantity. Let this vector quantity be a vector C, which is normal to both A and B, such that A, B, C form a right-handed system or a Cartesian system. This type of frame we get where A and B are two right-handed system. Okay, and C the vector after getting A and B, A cross B form the right-handed system, and C is normal to both A and B. This is in a two-dimension plane. Otherwise, this dotted line should be perpendicular to both A and B, so it should be orthonormal. Okay. In vector calculus, we already seen A cross B denoted by a vector quantity that is C, and finally after cross product we get AB sine theta and cap. AB is again an scalar. Sine theta, after giving the value, numerical value of theta, sine theta becomes again numerical. But n cap, unit normal vector, by producing a scalar quantities is again a vector quantity. Therefore, C is a vector. How we solve the question of cross product? As we see earlier in vector analysis, C equals to A cross B equals to, in place of E1, E2, E3, you have rememorize IJK. Okay. In earlier classes, you have taken IJK. But in case of continuum mechanics, we already in our starting lecture, we have given that IJK can be written E1, E2, E3 in continuum mechanics. So E1, E2, E3, and in second row, the component of A, if it is in three dimension, component of A are A1, A2 and A3, and the same component of B are B1, B2, B3 represent in the determinate notation E1, E2, E3, A1, A2, A3 and B1, B2, B3. Okay, we know that C is a vector quantity, so C must be written in the form of C1 E1 plus C2 E2 plus C3 E3. And early in earlier classes you have written C1I plus C2J plus C3K. So just rememorize the earlier, and by changing IJK to E1, E2, E3, you can easily find C is nothing but C1 E1 plus C2 E2 plus C3 E3. But by opening the determinant, this we get E1 and uh, minus A2 A3 B2 B3 determinant of two order, that is A2 B3 minus B2 A3. Okay, so E1 the component of E1s are A2 B3 B2 A3 where plus E2 when we open the E2, then A1 A3 B1 plus A1 B3. Okay, but it is on a second component, so minus sign should be there. So this is E2 A3 B1 minus A1 B3. Okay, for third case E3 we have A1 B2 minus B1 A2. So we get these three component. By equating this, we get C1 is nothing but A2 B3 minus A3 B2. Similarly, C2 is nothing but A3 B1 minus A1 B2, and C3 is nothing but A1 B2 minus A2 B1. The one thing common we have observed here, that we have taken C1 in terms of A, B, nothing indices are similar to 1. Here we see A2B3 minus A3B2. 1 is not coming. Okay, similarly in C2, 2 is not coming in with A and B. Similarly in C3, 3 is not coming in A and B. Okay, so these are the three components of vector C. In order to express these three components in index notation, we introduce a permutation symbol epsilon ijk, which we already studied in last lecture. Now again we discuss. We know that Eijk permutation Cartesian tensor in three indices having three values 1, 0 and minus 1. 1 when ijk perform even permutation. Okay, this means Eijk is equal to Ejki is equals to Ekij. These are Ijk, Jki and Kij are the even permutation. That's why the value of all three becomes 1. But in case of epsilon ijk equals to minus 1, when the ijk form odd permutation. Okay, in such case Ikj, Kji, Jik, that is minus 1. Okay, but when they doesn't form any permutation, in such case we have epsilon ijk is equals to 0. Here for example point of view, they are given these three values clearly explainable. Epsilon 1 2 3 2 3 1 3 1 2 should be 1, because 1 2 3 2 3 1 3 1 2 are even permutation. But in 1 3 2 2 1 3 3 2 1 are odd permutation, that's why minus 1. But in case of 1 1 2 1 2 2 1 3 3, no permutation framing, that's why it's taken value 0. So again we discuss C1 is A2 B3, already we have taken in 1.4.2. So C1 is A2 B3 minus A3 B2. So in index notation, we may write C1 is nothing but epsilon ijk aj bk. Okay, epsilon ijk aj bk. When we substitute epsilon ijk even permutation, it takes the value I should be 1, j should be 2, k should be 3. So this become A2 B3. But if we write epsilon I should be 1, jk interchange, so it become minus. So this again becomes A2 B3 minus A3 B2. So C1 can be written epsilon ijk aj bk. Similarly C2 may be written epsilon 2jk AJBK. Similarly, C3 may be written as epsilon 3JK AJBK. After giving the value, I should be fixed in C3. C3 is 3. In C2, I is 2. In C1, I is 1. So, in general form or in general case, what we are observing that whatever the value we have taken for I in cross product, it's changed into different values. J and K are taken different values. So in general way, if we write AI cross BI in index notation, should be a cross product of AI and BI is equals to CI, a vector quantity, and in index notation it may written as epsilon ijk aj bk, where ijk are running here in three dimensions. So ijk taking the value from 1 to 3. Okay, so this is in a vector notation of cross product. AI cross BI is nothing but epsilon ijk aj bk. I should be the component of CI vector. J and K are the aj and bk's notations. Okay, so it should be remember in other topics we are taking right directly. Whatever the cross product is nothing but of two vector a and b, or if they are vector r and s, we may write epsilon ijk rj sk. Okay, whatever we have to given vector, according to that, I should be the first indices, epsilon ijk, jk should on the two vectors, whatever the vectors given. So this is the standard notation of vector or cross product. Okay. Now we are taken some example numerical in which first example is find the volume of a rectangular parallelepiped. Okay. Volume V of a rectangular parallelepiped is given as, in earlier classes we already seen, if V is a rectangular parallelepiped, then V is nothing but A dot B cross C, where A, B, C are the continuous edges of rectangular parallelepiped. Okay, so A dot B cross C. Here what we are doing, we are taken the quantity B cross C. Let us suppose B cross C, the cross product of two vector B and C is, let us suppose, that is denoted by D, because we know that the product of two quantity is again a vector quantity. So we are given B cross C equals to D bar. Okay, that D vector should be placed in, again, V equals to, in first equation, V volume equals to A dot D. Okay, and in earlier lecture we have seen that dot product of two vector is nothing but A dot B is what? AI BI. So here A dot D what becomes? AI DI. Here we take dot and cross product both simultaneously. So it is a very good example of dot and cross product. First we taking B cross C, a cross product denoted by D, and A dot D is nothing but dot product denoted by AIDI. Okay. From earlier slide, we know that DI is what? Cross product of B and C. So how it is written? DI epsilon ijk bj ck. Okay, because the vector in cross product are B and C. So DI is nothing but epsilon ijk bj ck. Substitute this value of DI in the volume formula. So V becomes AI epsilon ijk bj ck. Okay, epsilon ijk is an scalar quantity, so we may write V is nothing but epsilon ijk ai bj ck. Okay, this is in a volume of a rectangular parallelepiped. Very simpler way. In case if we solve by vector algebra, it is a very lengthy question. But in index notation, it's become in a very small way to represent as easier in index notations. Okay. One more example we have taken here. What we are seeing, the question is determinate A, or it may written as determinate Aij, is nothing but may be represented as epsilon ijk a1i a2j and a3k. this we have to prove, and this is a very fundamental law which we use in a very important inequality that is known as Epsilon Dale and inequality, which we studied in our next lecture. Okay, so this is a very important relation which we use in our future lecture. How do we take, we we know that scalar triple product of the three vectors is in earlier slide, or a volume of a parallelepiped. We already seen A dot B cross C. How it is represented in determinate notation? A dot B cross C is A1, A2, A3, B1, B2, B3, C1, C2, C3, and A, B, C, 3, all three are vectors. So it is denoted as A1 E1 plus A2 E2 plus A3 E3, be denoted by B1 E1 plus B2 E2 plus B3 E3. Similarly, C denoted by C1 E1 plus C2 E2 plus C3 E3. Left hand side of the very first equation, A dot B cross C, in which we suppose B cross C is D. Okay, so again it becomes A dot D, that is nothing but AI DI. Okay, and DI is B cross C, that is a cross product of two vector B and C. So in index notation, Di can be represented as epsilon ijk bj ck. This is substitute again in A dot D or AI Di. In place of Di we may write, so it becomes epsilon ijk AI bj ck, where AI bj ck are the three vectors. Okay, so again now we take, if AI is denoted by A1i, Bj denoted by A2j, and Ck denoted by A3k, then our from equation 1 and 4 we get this relation epsilon ijk a1i a2j a3k, or in place of a1 a2 a3 b1 b2 b3 c1 c2 c3, suppose putting these values, so it becomes a11 a12 a13 a21 a22 a23 and a33 a32 a33, that is determinate aij. So a determinate aij is nothing but epsilon ijk a1i a2j a3k. This we have to prove, and very important inequality, that a determinate can be written as in index notation epsilon ijk a1i a2j a3k. This is a very important inequality which we use to prove further inequalities, in which one is very important, epsilon Dale identity, which we prove in our next lecture. So for today we have sum up to there. Thank you.